Okay, I'm working on the homework here for 10.8. We're doing numbers 1 through 4, 11 through 14, 15, 16, and 19. So let's look at number 1. We're asked to find the length of the curve. So they give us r of t equals this three-dimensional vector function t, 3 cosine t, 3 sine t. And they're looking for the length of this on the interval where t is an element of the closed interval -5, 5. So what we know is that the length of the arc length of a vector curve is given by this formula. So what we need to do is find the magnitude of the derivative and then integrate it from a to b, where a is going to be -5 and b is going to be 5. So let me do some work over here. First of all, what is the derivative of this vector function? Well, the derivative is just going to be 1, -3 sine t, and 3 cosine t. So we're just taking the derivative of each component function. And now the length of this derivative, or magnitude, is going to be the square root of each of these components squared. So 1 squared is 1, plus when you square this you get 9 sine squared t, and when you square this you get 9 cosine squared t. And then this is equal to square root of 1 plus, let's see, can factor 9 out of both of these, 9. I'm left with sine squared t plus cosine squared t, which of course is just 1. So this is just 9 times 1, it's 9, plus 1, that's 10. So root 10. That's the magnitude of the derivative. So I just come over here now, I'm going to integrate -5 to 5, square root of 10 dt. That's about as straightforward as it's ever going to get. So let me go ahead and do that work now. The antiderivative of root 10 with respect to t is just equal to root 10 t, and we're going to evaluate that here. So now what we do is just plug in 5, subtract what we get when we plug in -5. So if I plug in 5 right here, I get 5 root 10. And if I plug in -5, I get -5 root 10. And if you subtract negative, it's adding, so we're just going to have 5 of these plus another 5, so that's 10 root 10. Whatever that is as a decimal. You could go figure out what that is as an approximation, but I'm just going to leave it like that. Okay, let's move on to, let's see, number 2, number 3, number 4. They're all the same. Let me do 4 since it looks a little different. The vector curve doesn't have sine and cosine in it, so let's take a look at this one. It'll be the same formula. So we have our vector function is 12t, 8 t to the 3/2, and then 3t squared. We're looking here on the interval. I'll write it the other way this time, the way they have it in the book. All right, so same story. We need the derivative. Let's go ahead and get the derivative right here. Derivative of 12t is 12. Here we have to use power rule, so this comes out 3/2 times 8. That's going to give you 12 t to the 1/2, since we subtract a 1 from that. And this one's just going to be 6t. Now I need the magnitude, which is square root of each of these components squared. So 144 plus, if we square that, we get 144t. And then here, if we square this, we get plus 36t squared. And at this point, should be able to factor out something here. Let me do it this way. The square root, let me put it in descending order. 36t squared plus 144t plus 144. So how many times is 36 going to this? What, 4 times? So if we pull out a 36, we get t squared plus 4t plus 4. 120. All right, 24. Yeah. Okay, plus 4. And then we can pull the 36 out of the root and get 6 root, and then t squared plus 4t plus 4. And this looks like possibly a perfect square trinomial. I'm going to continue this up here. Just remember we're between 0 and 1. So from here we get 6, and then underneath there, isn't that the same as t plus 2 squared? So if you take this and square it, you should get this. And so now you're taking this square root of something squared, so you get just the t plus 2. I mean, technically we should be looking at the absolute value of this, but because t is a positive number, this will always be positive, so I don't have to worry about that. So that's the magnitude of the derivative. So we come back over here, the length is going to be equal to the integral from 0 to 1 of this, which was 6. I'll just pull the 6 out now. And then t plus 2 dt. And then this is just equal to 6. And now the antiderivative of t is 1/2 t squared. The antiderivative of 2 is 2t. And we're evaluating this here. Let's plug in 1 first. If we plug in 1, we get 1/2 squared, it's 1/2. If we plug in 1 here, we get 2. And then minus 6 times, if we plug in 0, this is 0 and 0, add them together, we get 0 times 6, so it's going to be 0. So our answer should be 6 times, let's see, put those two together, what's that, 4/2, 5/2. And then if we multiply there, 3/15, we should get 15. So for number 4, we should get 15. Okay, so I'll let you do 2 and 3 on your own. Let me see, do I want to do anything else in there? Find the length of the curve, correct to 4 decimal places. Nah. Hmm, 7 looks pretty good. Let's take a look at 7. I think 7's, it's not on your homework. I'm going to add it to the homework today. So on number 7, it says, let C be the curve of intersection of the parabolic cylinder x squared equals 2y, and the surface 3z equals xy. Find the length of C. Find length of C from the origin, which is the point 0, 0, 0, to the point 6, 18, 36. All right. So what we need to do is somehow come up with a vector function that draws the intersection of these two surfaces. So let me try and draw, well, I don't think we need to draw the surfaces, but let's try and come up with our R of t first. It's going to be 3 component functions. So let's try and get some relationships here. I know that z is going to be, or 3z is going to be x times y. This has x and y in it also. So what I could do is let's let the x component, let's just let the x component be t, okay? So t is really like the x, okay? So imagine that each of these x's is really a t. So this really would become something like t squared equals 2y, and this would become 3z equals ty. All right, well, on this first one, I can solve this for y. So if I solve this for y, I get 1/2 t squared equals y. So now I know what y would have to be. Y would have to be 1/2 t squared. So again, if the x coordinate is t, then the y coordinate must be this, and that would make it live on this curve. And now over here, I look at this one, let's solve for z. Z is equal to 1/3 t times y, but in order to live on the intersection, this y has to coincide with that y, so I'm going to replace this y with 1/2 t squared. And so what we get is 1/6 t cubed. So if we graph this, right, if we start graphing this vector curve, then it should draw the intersection of these two surfaces, because every point on that curve satisfies this equation and satisfies this equation at the same time. So there's our vector function. Now what we need to do is we need to figure out our restriction on t. So t is between a and b. That way we can draw we can set up the integral. And what we know is that we want to start at 0, 0, 0. So can you think of a t that I could plug in that would give me 0, 0, 0? Hopefully that's obvious, 0, right? And then you want to think of a t that I could plug in that's going to get me this point, 6, 18, 36. Well, look, the first component function is t. I need it to be 6, so a good candidate for that is 6. Let's just check it. 6 into here is 6. 6 here is 36 divided by 2 is 18. And then 6 cubed divided by 6, yeah, that's 36. So we're in business. Now I'm going to do more of my preliminary work here. I'm going to go ahead and take the derivative of this, because I'm going to need the magnitude of the derivative. The derivative is 1t 1/2 t squared. That's the derivative of that. And then I take the magnitude of this, which is square root of 1 plus t squared plus 1/4 t to the 4th. And I'm going to hope that this factors. So is there a way that I can get this to factor into a perfect square trinomial? So let's try this. I'm running out of room. How about 1/2 t, 1/2 t, and then 1 here and 1 here, plus here, plus here. Does that work? So we multiply the 1/2 times 1/2, we get 1/4 t to the 4th, so t squared, t squared. So do that, we get 1/4 t to the 4th, good. We do 1/2 t squared times 1 is 1/2 t squared. 1/2 t squared times 1 again is another 1/2 t squared. We add those together, we should get a t squared. And then 1 times 1. So that works, good. So since they're the same thing, take the square root, we just get 1/2 t squared plus 1. So I'm ready, integral time. So what I'm going to do now is say that the length of this is going to be the integral from 0 to 6 of that, 1/2 t squared plus 1 dt. Take the antiderivative there, you get 1/6 t cubed. Antiderivative here is just t, 0 and 6. I already know when I plug 0 in, everything's going to go away. So all I have to do is really just plug in 6. So plug in 6 into this, you get 36 plus 6 here, you get 6. Should be 42. 42 units, whatever the heck 42 units is. All right, pretty cool problem. I'm going to add that in there. 7. All right, let's do number 11. That's next. I don't think I put number 7 up there last time. Oops. I need to remember to write down the number. All right, so for 11, suppose that you start at the origin, you start at the point 0, 0, 3, and you move 5 units along the curve. X is sine t, y is 4t, z is 3 cosine t in the positive direction. Where are you now? All right, so I'm going to try and draw this a little bit. X, Y, Z. So we're starting at the point 0, 0, 3. So 1, 2, 3, right? And we're moving along this curve. Oh, I think I forgot the 3 in front of the, did I forget the 3? Yes, I did forget a 3 right here. 3 sine t. So we talked about this in class that if you have like 3 cosine t, 3 sine t, that should draw a circle. And since I'm using the x and the z variables, that means it's going to draw a circle in the xz plane. And then the y coordinate is a linear function, which means that I'm going to try and draw circles, but at the same time I'm going to be going out the y-axis. So it's going to create this, not a spiral, but it's like a helix. It's on the outside of a cylinder. And it starts here, all right? And so imagine just coming down the y-axis with a circle, but it starts here, so no matter how you draw it. So that's coming out this way. So what we're saying is we're starting at this point, we're moving along this curve, and you're going to move a total distance of 5 units. So that means that you move 5 units along the curve, okay, whatever that is, that's 5 units. And it wants to know now, you know, where are you? What point is that? Question, question, question. So where are you? So this is kind of a backwards problem. This is actually the arc length that you've traveled. I know that to do an arc length problem, I need to integrate from A to B, and I need to integrate the magnitude of the derivative, dt. If I'm starting at the point 0, 0, 3, then I need to figure out what A I would plug in to start me out at that point. So let's see if we can figure out what A is. A would have to be what? So what do I plug in here for t, t, and t to get 0, 0, 0? Again, it's pretty obvious. Look at the y coordinate. The only way that that's 0 is if t is 0. So if t is 0, we get 0 here. If t is 0, sine of 0 is 0, so that would be 0. And if t is 0 here, cosine of 0 is 1 times 3 would give you 3. So I know that it'll start here, right? But the question is, where does it stop? And that is the question. I don't know. Okay? That's what the question's asking for, is what point do you stop at? The point I stop at coincides to some point in time, which is the B. So I'm going to have to set everything up, except I'm going to wind up solving for that variable. So let's just set this up. Let me go ahead and get the groundwork taken care of here. So let's take the derivative. What is the derivative of the vector function? Now I didn't write it in vector form, but these were the parametric equations. So I'm just going to go derivative, derivative, derivative. So we have 3 cosine t, 4, negative 3 sine t. And boy, we love to see those sines and cosines in there because we know Pythagorean identity is probably going to come into play here. Square that, 9 cosine squared t, plus square that 16, plus 9 sine squared t. We can do the same thing we did earlier. We can take this one and this one, factor a 9 out. The rest will become a 1. So I'll have a 9 plus a 16. That's just root 25. And that's just 5. Awesome. So here's what I know. This right here equals, for me, integral from 0 to b, which again, I don't know what b is, of 5 dt. Right? That's the length of the curve if I go from 0 to b. Well, I know that I'm supposed to go 5 units, right? So I want this to be equal to 5. See, this is what I want. Okay, I want to figure out what b I need to stop at. What point in time do I need to stop at in order for this arc length to be 5? Well, again, let's take the left side of that equation, okay? The left side of that equation is just 5t, that's the antiderivative, evaluated 0 to b, and we need that to be equal to 5, right? So I'm working like left and right hand side down like this. If I plug b in here, I get 5b, and if I plug in 0, I get 0, so I subtract nothing. I need that to be equal to 5, which means b must be 1. That's it, b is 1. So if b is 1, I should have traveled a length along that curve of 5 units. But the question is, where are you now? So we need to go back and we need to plug b into the parametric equations, or into the r function, not the derivative, but the original one. So I want to know what r of 1 is. So I'm just going to look at the derivative. The original function was 3 sine t, so it's 3 sine of 1. And then it was 4t, so 4 times 1 is 4. And then 3 cosine of 1. That's what you get. So if we look at this as a point, it's just 3 sine 1, 4, 3 cosine 1. That's the point that you're at. That's where you are on the curve if you travel 5 units along it, if you had started at 0, 0, 3. Or which one was that one, 11? Okay, I've looked at 12. I'm going to scrap 12. Let's not do 12. I think it's a nice problem. You can try it on your own, but we really aren't covering anything like that in class, and I can kind of see the value of the problem, but let's skip 12. So skip 12. And that'll move us into number 13. So for number 13, it says to find the unit tangent and the unit normal vectors. And in the assignment, I say to only just find t. All right, so let's look at number 13. R of t equals the vector t, 3 cosine t, 3 sine t. All right, so we're trying to find the unit tangent vector. So we're trying to find this vector right here. By definition, this is the derivative vector divided by its own length. So the derivative of this vector function is 1, negative 3 sine t, and then 3 cosine t, but I want to divide that by, or scale it by, its own length. So the length of that is, length of this is 1 plus 9 sine squared t plus 9 cosine squared t. And if you work this out, you're just going to get root 10. So essentially, you're going to take each of these components and divide by root 10. So you get 1 over root 10, negative 3 over root 10, sine t, I'm running out of room, 3 over root 10, cosine t. See if that came out on the video. I think it's pretty darn close. All right. So that is the unit tangent vector, capital T. And we can just leave that written that way. I don't see any need to go any further. Now, is that all at once? Does it want it at a certain point or anything? No? Okay, so now I don't ask you for the unit normal vector, but I'm just going to show you like how it would be done on this one only. So the unit normal vector is going to be, by the definition, it's the derivative of this over its own length. That's all it is. It's just, we're basically doing the same thing we did on R, we're doing the same thing on T. So T is this right here. So we first take the derivative. The derivative on the top would be, well, that's nice, derivative of that 0. Derivative of this is going to be negative 3 over root 10 cosine t. And then if we take derivative of this, we get negative 3 over root 10 sine t. And we want to divide that by its own length. So we have to find the length of this. Let me do that just up here. The length of this is going to be the square root of this squared, which is 1/10, plus this squared. You square the negative 3, you get positive 9 over 10, so 9/10 sine squared t. And then you square that, you also get 9/10, but cosine squared t. Look at these two. Factor out a 9/10. Use the identity, it turns into a 1, so you wind up getting 9/10 here, plus 1/10 is 10/10, which is just 1. And so, oh, you know what? Crap. I'm doing the wrong thing. Sorry. Oops, I was doing the magnitude of this. Obviously, the magnitude of this is 1. It's a unit tangent vector. I need to be taking the length of this. All right, so what's this length? Because that's what this is down here. All right, so square root of this squared, nothing, don't worry about it. This right here, 9/10 cosine squared t plus, again, 9/10 sine squared t. And if you factor out the 9/10, we just get 9/10 here. And square root of 9/10 is 3 over root 10. So we're going to take this, we're going to divide it by 3 over root 10. So let's see what that turns out to be. What am I hitting here? So we take each component and divide it by this. So 0 divided by that's still 0. This divided by this, the roots, the 3 over root 10 cancels. We just get negative cosine t. And then here, again, the 3 over root 10 cancels. We get negative sine t. There we go. So that's what you would get had you actually been asked to find the unit normal vector. I might actually ask you to do that now that I think about it. I think that's a good exercise. Yeah, I'm going to edit that also. I think it's worth doing. Now for part B of the problem, you're supposed to use formula 9 to find the curvature. So let me see formula 9, where is it in here? Definition, formula 9. So I'm used to supposed to use formula 9, which is that the curvature K of t is going to be the magnitude of t prime t over the magnitude of r prime t. There. So we're going to use that formula. And we just found those. All right. So we just did both of those. The top one, the magnitude of this was that right there, 3 over root 10. And then if you go back and look further back, the magnitude of the derivative, we had, where the heck is it? It was it was just root 10. This was root 10. And so if you simplify this, take this, take a fraction, flip it, you just get 3/10. So the curvature would be 3/10. All right, that's number 13. Number 14, 15, and 16 all work the same exact way. I'll leave you to do those on your own. But I will look at number 19. So I'll leave that there. Number 19, well, I'll erase it. Number 19, it says find the curvature again, but it says use a different formula. So let's take a look. We have r of t equals 3t, 4 sine t, 4 cosine t. So 3t, 4 sine t, 4 cosine t. Let's see if I got that right. Yes. Okay, so find the curvature using the other formula. So the other formula is, let's see, theorem 10. Where is there theorem 10 in here? Yeah. So we have that the curvature can also be found by taking the magnitude of the cross product of the first derivative with the second derivative all over the first derivative cubed magnitude. All right, so in order to do this using that formula, we need a couple of things. The derivatives first. So what's the derivative of this vector function? Well, it's 3, 4 cosine t, negative 4 sine t. I'm going to give myself a little more room. R prime t is 3, 4 cosine t, negative 4 sine t. And then underneath this, I'm going to put the second derivative because I'm going to have to cross them, take a cross product. So derivative of this is going to be 0, negative 4 sine t, and then negative 4 cosine t. And now let's cross these two. So I'm going to actually do their cross product here. So in order to find this piece up here, which is r prime crossed with r double prime, I'm going to get a vector. Let's see if I can do it. If I cover up the I and do this, I get 4 cosine t times negative 4 cosine t, which is negative 16 cosine squared t. Then I want to subtract from that negative 4 sine t times negative 4 sine t. So that's 16 sine squared t, but I'm subtracting it. So minus 16 sine squared t. If I factor out a negative 16, then I have cosine squared t plus sine squared t. That's going to be a 1. So this is just negative 16. And then I'm going to cover up the j. and do this again. So this times this, negative 12 cosine t. All right. And then 0 times that is, it's gone, so who cares? So I get negative 12 cosine t, but since it's the j, I need to change the sign, so it's going to be positive 12 cosine t. And then I cover this up, and I do this times this, which is negative 12 sine t. This times this is 0, so it doesn't matter. So negative 12 sine t. Okay, so there's your cross product. Now I need its magnitude. So the magnitude of this is going to be, well, start squaring things away here. Let's see if I can do this any easier. This is 19. Yeah. All right, so 256 plus 144 cosine squared t plus 144 sine squared t. And then these two together, when we do all the work, we get just 144. And then plus 256, that's 300, 400. So we get root 400, which is 20. So what we have at this point is that this is equal to root 400, which was 20, over, now we need the magnitude of the derivative, which was right here. We need to find its magnitude, which I'll just do right up here. R, I, T, I need its magnitude, so it's square root of, let's see, 3 squared 9 plus 16. This is kind of broken record at this point. We've been getting the same thing happening on all these. So they have to pick these very carefully so that they work. So if you do this, you'll get a 16 here, and then plus the 9, it's going to be 25, and square root, that's 5. So you get a 5 down here, and the magnitude of that, or sorry, that cubed, right? So 5 cubed. So what happens here? You get 4 over 25, I believe. Yeah, 4 over 25. That looks right. Yeah. So your curvature is 4/25. All right, I think that'll do it for this section. See if there's anything else here. Yeah, let's let that be it for now. I've got things to do.